This is my Physics 2212 Lab 4. So the purpose of Lab 4 is to use a simulated virtual circuit to simulate voltages, currents, and resistances. Before running the simulation, we utilized the loop rule and the node rule with knowledge of current conservation in order to predict and solve for readings on ammeters and voltmeters. The node rule is that the current entering a node is equal to the current leaving a node, and the loop rule states that the potential difference around any closed loop is equal to 0. So part 1 of lab procedures. The first simulated experiment involved two 1.5 volt batteries, 2 resistors, and 2 ammeters in a circuit. When run in the simulation, the ammeters read 0.02 amps. This is very similar to the predicted measurement using I equals V over R. When the ammeter was inserted backwards into the simulation, the reading was the same, but the sign flipped. When replacing an ammeter with a voltmeter, the potential was 3 and there was no current. This is because the current will not be able to flow through the voltmeter, so the potential is equal to the EMF. The sum of potential difference should be 0 according to the loop rule. So the actual sum in this scenario is also 0. When attaching the voltmeter, ammeter, the ammeter reading doesn't change because of the voltmeter's high resistance. When the ammeter is placed in parallel with a resistor, the current increases to 0.06 amps. This is because placing a resistor in parallel lowers the equivalent resistance. So plotting the voltage with respect to location from the EMF, we can see that through A through B, the voltage change is 3. B through C is 0. When encountering the resistors, it decreases from C to D, stays the same from D to E, and then decreases again from E to F, and remains 0 from F back to A. Calculating experimental resistances, we use that R equals the potential difference divided by the current. So the resistance from the 47 ohm resistor was 47.95. The resistance from the 100 ohm resistor was 102.05. The resistance of the wire is equal to the resistance from the ammeter, which is equal to 0. Part 2 involved the RC circuit. In a circuit with a battery, a bulb, and a capacitor, the bulb will be immediately brightened and then fade out. When discharging a capacitor, the bulb behaves very similarly. Current starts at a maximum, goes to 0 as time goes to infinity. This is the data from the time charging capacitor and the time discharging the capacitor. So we want to define the time constant, which is RC of the circuit. This is when the voltage distance has dropped to 1 over E of its original value. The theoretical RC equals 30 ohms times 0.2 farads. So for the experimental time constant, based on energy conservation, the loop rule, we can deduce that the plot of the natural log of delta V over delta V naught versus time should yield a straight line with a slope of negative 1 over RC. Plotting our values on a graph yields a slope of negative 0.1667 and a time constant of 5.9998 seconds, which is very close to our theoretical calculation of 6 seconds. For lab questions, we were asked if we were doing this lab in real life and use an actual ammeter instead of a simulated one. The resistance in a real ammeter would not be exactly 0, so the real life current would be smaller than the simulation. If we were to do this lab in real life and used a real battery to charge a real capacitor with no resistance in the circuit, we would have capacitors and wires that all have some internal resistance. So the capacitor would charge more slowly in real life.